AlbuSchaeffer, thank you for coming at 8 o'clock after the beer yesterday. Well, I'm the director at the DLR Institute, so thank you for being yesterday there, but I'm still trying to do also some own research, and it's my first time on at dynamic walking, so I would like to talk about some things which I still think most of the robotics community does not know much about. Nonlinear oscillation modes of conservative systems and how it can be used for locomotion. Okay, so the motivation is well known. Biology uses the interplay basically between kinetic energy and potential energy to recycle energy over the gates. And this is a highly nonlinear process, right? And in engineering, we were taught about linear modes. Everyone knows about linearization and linear modes. But what about nonlinear oscillations? And we have seen yesterday already a beautiful video, and I'm referring now again to David's work, was shown that, for example, for a quadruped, all the typical gates of quadrupeds can emerge. I think they have done it by pure optimization for some simplified models, so zero foot mass and so on. But for a conservative system, right, you can find initial conditions such that those gates are just intrinsic motions of the coupled multi-body and elastic system. So the question is, it's remarkable actually, because on the other side, our engineering intuition about multi-body coupled systems, like a double pendulum, for example, is they are chaotic, right? And you can find on YouTube these kind of videos really showing chaotic behavior, right? And if you simulate that, you see this kind of chaotic behavior and very complex behavior. So how does this intuition or experience of rather chaotic motion, if you have almost no damping, relates to the existence of these periodic motions as well, right? This was the intriguing question actually I asked myself in my ERC grant, which will come to an end next year. And of course the analogy, we model muscles and bones by spring dampers and multi-body systems, right? And it turns out, or for me it turns out, that the mathematical tool to analyze those nonlinear oscillations is differential geometry and in particular Riemannian geometry on manifolds, of course. So we are looking for periodic motions, but of very highly nonlinear systems, and to ask under which conditions do they exist and how to find them and so on. Right? This is the main part I will talk about. And the basic notion to introduce here is geodesics. I assume all of you know, maybe the people with a biological background don't know so much. What's a geodesic? Well, the geodesic is the shortest point, the shortest path between two lines, and you get it by optimization. Of course, in Euclidean space, it's just a straight line, right? But you get it by optimizing the integral of the norm of velocity, or of the square of the norm of velocity equivalently over the entire path, right? Of course, if you are a manifold on something which is curved, there's no straight line, right? So what's the shortest path? Well, on a sphere, we know it's a part of a big circle, right? But what's on an arbitrary surface? Well, that it's not a straight line you can see over here. So probably when all you guys flew in from US, you took such a path, which is not a straight line, but is the shortest path on that map, just because of the curvature of the Earth, right? So this is the directions airplane state. Well, and if you take as a norm for velocity, actually the mass matrix, then you have kinetic energy basically, right? And the shortest path in terms of, you can define specific matrices, and this brings us to the link actually between geodesics and multi-body dynamics. Because we have the Lagrangian system, and then first of all just consider pure kinetic energy, right? And we know that the principle of least action just tells us nature minimizes the integral of the Lagrangian function, and if you have pure kinetic energy, then you minimize the integral of kinetic energy, which is just a geodesic in terms of kinetic energy. So basically you can say that such a double pendulum is the same thing as the motion of a point mass on a manifold which is curved by the inertial tensor. By the way, you know, we are not doing relativistic robotics here, but Einstein used the same interpretation in a different setup. But the idea is the same, right? That a variation of the metric tensor can be represented as a space which is curved, and then you get rid of all this multibody, you just have a point mass and some curved surfaces, right? And so the trajectory of freely moving multibody systems, which are conservative, everything goes for conservative, are geodesic with respect to the inertial tensor. I mean, for people just used to motion planning, we know, right, that having a cost function which varies leads to shortest paths which are variable. Now, the question is, what if you have potential energy? How does this change? Well, this is known also since the time of Jacobi, actually. It's the same with the Jacobi matrix, but he defined also a Jacobi matrix, and instead of just using kinetic energy, you use this metric, which is, well, 2 is for historical reasons, but the constant energy minus the potential energy times the mass matrix. And so this is your cost function, so to say, right? You minimize the path under this cost function. And the interesting thing about that is that you can reduce then the motion of a multibody system in potential field to just the motion of a point in a curved configuration space, right? So let's see what insight springs this. Well, the main point is that mathematicians have looked at periodic geodesics of all kinds of manifolds for more than 100 years, right? And there's an incredible amount of mathematical theory of existence of periodic geodesics. So for us, of existence of periodic motions in, you know, for multibody systems. And the classical thing, which you know, they give us an example is, and I saw that in the book of Arnold like 20 years ago, and I wondered about that, is if you take a double pendulum and you take two numbers, n and m, you will always find the periodic trajectory of this double pendulum, which turns n times around joint 1 and m times around joint 2. And the explanation is just take a rubber band, wrap it around your torus, which is the configuration space, let it contract to the minimum length. Well, this will be your closed geodesic.
This is without gravity.
Without gravity? No, it's with gravity, because if you take the Jacobi metric, it's with gravity. Gravity, elastic springs, put whatever you like, potential kinetic energy. If you have gravity, you put the Jacobi matrix. If you don't have gravity, you just put the mass matrix, right? So it holds for what interests us, right? And then I asked Arne, one of my PhD students, show me those double pendulum with the trajectories and, you know, contract those rubber bands. I want to see them. But and these are, you know, for n and m, 0, 1, 1, 1, and so on. All these pairs, right? That's how they look on the torus. You just let it contract because the matrix is, as I said, variable. They take some strange shape. But you would like maybe to see how they look like. 0, 1, 1, 0, another 0, 1. So they are not unique. The theorem is telling you that at least one exists, that sometimes there might exist a lot of them, right? And of course, remember we started from saying the double pendulum is chaotic. Yes, it's true. Mathematicians tell me that in the middle of chaos there are some theorems that you have isolated points of stability, right? Okay. Even more of them, they start to be, you know, funnier and funnier. 1, 1, 1, 2, 2, 1. Remember, these are intrinsic motions. You don't put any power into it because you assume that they are not dissipative. This is what a double pendulum does by itself, and you can go up to any dimension, right? They exist. Even more of them. Let's see if, oh, I'm sorry. Where was it again? Oh, the animation is too slow. Okay, what about 0, 0? So those who, because our joints don't turn endless, right? So are there some periodic motions which don't do 2 pi motions? Plenty of them. You can find plenty of them. Again, using rubber band contraction instead of Poincaré-Mach or multiple shooting. Valid only for conservative systems, right? And then now the first application, which is related to robotics. There's a beautiful paper of Hatton and Chusett. They have analyzed, you know, how to move this kind of a snake robot with non-holonomic constraints to maximize velocity. Well, we asked ourselves, if I would put some springs in there, could you find some periodic motions where, assuming you have no friction, it will oscillate by itself and move forward? And this is one of the solutions, right? You see the snake over there. You give it some initial condition. This is the trajectory and configuration space, Q1 and Q2. They have shown that you need to, kind of maximize this area due to the green or generalized Stokes theorem, right? But you can find that. Okay. Then, even more, so far we talked only about trajectories which are of circular shape, so it's like, those curved flows. There are, however, a big class of curves which have line shape, so, they have two endpoints. These are the two topologies curves can have. And it turns out that they are the generalization, actually, of the modes, of the linear modes I was talking before. And, linear modes we all know, right? In one dimension, x and x dot, and then you have some oscillation with constant energy, and then you will have, for a linear system, an ellipse. If you just look in configuration space, the system just goes on a line back and forth. That's what it's doing, right? If you have a 2 degrees of freedom system, like something like this, you'll have two lines corresponding to the two modes. One is the in-phase mode, one is the anti-phase mode, and the system will oscillate on those lines. What's the generalization to nonlinear systems? And we know, of course, everyone in engineering knows that for an n degrees of system, you have n such modes, at least. If it's the generated, it might have infinitely many. Now, the generalization for the nonlinear systems is just because your metric is, curves the space, you won't oscillate on a straight line, but you will oscillate on a curve. But that's it, right? So you can, if the amplitude goes bigger and bigger, linearization does not hold, but this property of you can find n lines on which the motion is extremely simple still holds. And, well, I realized that in mathematics, people call them break orbits or break trajectories. So, and they have the property, they start on zero kinetic energy, end on zero kinetic energy, and go back and forth. So this is an oscillation of an arm, of a leg, you name it, moving on such a break orbit. And there's a guy called Seifert from Heidelberg in 1948. He has proven that for every multi-body system, you have at least one of such trajectories, and he conjectured that actually for an n degrees of freedom system, you have n, as for the linear systems. Mathematicians still struggle to prove that. You can find proofs of this theorem still today on arXiv, but we have a MATLAB toolbox where, given the dynamic model, you can compute all those n modes, and it seems that this conjecture holds, right? Well, if energy changes, those modes will also change. This is how they look again for our simple double pendulum, right? The cross there are the two linear modes, and then if you increase energy, they start to bend and bend. You can display it also in 3D. And this is how they look, again, for the double pendulum. You have one mode is this, which is the in-phase mode. The other mode is like this, or something like this, right? Okay, and how does it look for a more complex system? Now we come to our prototype there, right? If you attach the legs to the ground with ball joints, then you have 6 degrees of freedom left, and these are the 6 modes the system displays, right? And then, well, this is still preliminary, we didn't publish it, but if you release then the legs on some of these modes, the system starts to do this kind of things by itself, right? It's not a mode of the free-floating system, but of the fixed system, but still, it starts doing these kind of things. This is the most funny mode, and this somehow seems to go into walking. And well, Davide, I think he presented something about designing locomotion based on this kind of modes. How to, yeah, I make it. How to excite them, of course. They are not, we don't have conservative systems, so that's a central assumption. And this whole idea holds if you have systems which are close to little dissipation, right? And the idea is, instead of controlling things at 1 kilohertz, you would not control the swing by just taking by the hand and doing 1 kilohertz control, but you just input the kinetic energy you need to keep a constant level and let it swing on its own oscillation, right? That's the idea, which seems to, the simplest way to do it is with just some impulsive bang-bang control. And these are some videos, again, on this very preliminary system we have. These are the modes excited, and these are some first motions based on those modes. And with some of our previous PhD students, Dominic Akarosh and some other colleagues, we implemented, yesterday you have seen some of the motions. We can show that walking, trotting, galloping, you can generate around those modes, not exactly on those modes. I'm not completely happy, but you can generate some locomotion patterns. Well, George has shown you, he has a completely different approach. He's doing a planning for center of mass, and then the same with Johannes, and generating those trajectories. So we are looking at how to bridge this with oscillations, right? And we have some preliminary paper where the center of mass trajectory is we have a free parameter, which is the timing, and you take the timing from the oscillations. And the last link is to Antonin's point of, he is challenging us because he's doing everything with learning, and this works fantastically without any theory on oscillation modes. So he's setting the benchmark. You have seen the beautiful presentation yesterday. Still, I hope that this idea brought you some insight. I'm really curious to see your opinion on that. I've shown you a zoo of periodic motions, and the question is, how can we use them in locomotion? And finally, can we really use that also to maybe explain by the biological motion? Thank you very much for listening.
We're running a little bit late. We have 3 minutes for questions.
By the way, the three-body problem, these are periodic trajectories of the three-body problem, which is much easier than our oscillation of robots. Yeah, go ahead. Please, Anna.
Yeah, so what do you think about the role of muscles of using and benefiting from this underlying dynamics?
So, okay, if you assume, of course, muscles are springs and, of course, to some extent dampers, then you need to re-inject. So I ask myself, maybe are, the muscle distribution such that the stiffness matrix results in such a way that the modes correspond to something which is meaningful. There's also a hypothesis we are trying to verify. Yeah.
The extension to dissipative systems, when you have the feet leave the ground on those robots, there's energy lost. So you have to pump energy in. And your hypothesis is that when you take your conservative system and then perturb it with some dissipation and some injection of energy by some strategy, that you'll still get a continuation of those modes. That's kind of, that was a hypothesis you're making, is that correct?
Yes, I also said, the question is, do you think it's that it's a good idea to look first at a conservative template and then try to compensate energy? If your system is mainly dissipative, this idea doesn't work, right? So you need to build some robots which are close to, conservatives, and also design gates where you have little impact or...
Well, let's say the David Remy thing you showed, let's say those feet had mass, so that he couldn't have those solutions anymore because he would have dissipation. You think if you put in a little bit of energy by some random means, but fixed, you would still find his solutions, for example?
I hope. And the other point is, can you do some velocity matching to reduce the impact? Yes, but this is the main challenge. I fully agree, and Davide can tell you something about that. So many questions. I don't know, how should I take? Please, go ahead.
Yeah, maybe adding to this question, so have you thought about how to quantify the amount of dissipation? Because the more dissipation you have, but then you also get some coupling between different modes, right? So,
yeah. So the point is, what we have seen, a little bit of dissipation is good, because whatever error you put into the conservative system, it never forgets, right? The mistakes you have done once. If you have a little bit of dissipation, then this has some forgetting factor. So the best is you have a little bit of dissipation and re-inject the energy. If the dissipation is too big, then at some point, right, you better design your controller from the beginning, taking dissipation into consideration. So that's the big point to be debated about. I think. Yeah, please.
That's the last question.
Yeah. I'm sorry, coffee break. I'm happy to answer all the questions in the coffee break. Yeah. Please. The last question was still there.
Really briefly, I missed a little bit of talk. I was wondering, to do the rubber band contraction, what type of algorithm is that? Does it solve a PDE in order to do the contraction on the curved manifold?
Well, it's a different way, right? You solve it globally. Usually you integrate step by step by step, right? While for the rock-propelled contraction, basically you solve the PTE between the initial conditions at once, right? So still you have iteration, but instead of iterating in time, you iterate in space.
Yeah.
Maybe that's
But it is a PE.
Of course, it's still the differential equation. I'm not invalidating the Lagrangian equation, but it's a different way of solving it between initial conditions. By
He said it's a
iterating in
partial.
space in terms of time.
He says a partial differential equation, not an ordinary.
Yeah, yeah.
No, it's no.
It's an ODE.
It's an ordinary differential equation, but you have the conversions. I mean, the way of solving is different. The algorithm of finding the solution is different.
Okay, thank you.
Sorry, yeah, I didn't understand. Thank you.